Welcome you all to Principles of Organic Synthesis. So far we have studied carbon-carbon-carbon-nitrogen bond formation of aliphatic substrates, organometallic reagents, aromatic, electrophilic and nucleophilic substitution reactions, reactions of disodium salts and molecular rearrangements. In this lecture we will study the reagents containing phosphorus. If you look at the previous lectures, whatever we have studied, the formation of carbon-carbon bonds, carbon-nitrogen bonds, organometallic reagents, electrophilic aromatic substitution, nucleophilic aromatic substitution, disodium salts and molecular rearrangements, those reactions have been well explored. If you compare those reactions, the reagents containing phosphorus is new chemistry which has been started around 1950. Reagents containing phosphorus compounds also very important molecules which find broad utilities not only in synthetic organic chemistry, they also have broad applications in agriculture science and medicinal science, as well as they also have broad utilities in material science. And we will try to cover the utilization of organophosphorus reagents in organic synthesis. Now let us look at, as you can see here, this slide shows, as you can see here, this compound which contains phosphorus, which is known as sarin, which is a potent toxic nerve agent. If you happen to inhale, it damages the nerve system, leads to death, which is considered as a weapon for mass destruction. Now let us look at this compound. This also has phosphorus atom which is bonded with sulfur as well as oxygen. This compound is known as malathion, which we use as insecticide in agriculture field. In addition to that, we also use this compound to kill mosquitoes. Here some more examples are shown. You can see here this compound we use as biological membranes, and this one, the triphenyl phosphate, this we use as a plasticizar, and this compound, this is known as parathion. You have the phosphorus sulfur bond here as we have seen earlier, and this also we use as insecticide in the agriculture field. And this compound you can look at here, which has phosphorus oxygen and phosphorus nitrogen, this compound we use as in chemotherapy, and this phosphonium ion, and this is ylide, and we will often see the utilization of this reagent for the olefin formation. So as you can see here, phosphorus compound find broad applications in medicinal science, in biological science as well as agriculture science. As you can see here, this we use for chemotherapy, and this is we use as insecticide. And in addition to that, we are going to see the utilization of this reagent for the reaction with aldehyde and ketones for the olefin formation. Now let us look at the reaction of phosphorus. If you look at the periodic table, you have the nitrogen, then phosphorus. If you compare the reactivity profile of phosphorus with the nitrogen, phosphorus has a d orbital which it uses for the bond formation. The nitrogen doesn't have it. And if you look at phosphorus, it makes a strong bond with oxygen and sulfur. We have seen just several examples where you can see the phosphorus oxygen and phosphorus sulfur bond, and this and then if you, in addition to that, phosphorus 3 can be readily converted into phosphorus 5. Now let us look at the reactivity profile of phosphorus salt with ammonium salt. If you compare, for example, this phosphorus salt with hydroxide, it undergoes addition reaction. This hydroxide ion reacts with this phosphorus, and you will be able to form phosphorus of the phosphorus salt, and you will be able to have this addition product. Once you form this one, deprotonation of this can lead to the formation of this trimethyl phosphine oxide, and where you generate the benzyl carbon ion, which leads to protonation to give the toluene when we do the workup. And if what basically happens here, the hydroxide ion reacts with this phosphorus of the phosphonium salt, whereas you look at the quaternary ammonium salt, when you react with the hydroxide ion, it undergoes substitution reaction with this carbon, and here this acts as a leaving group, and the reaction goes via SN2 pathway, and instead of hydroxide ion reacting here nitrogen, it reacts with the carbon, and this trimethylamine leaves, and we get the alcohol as the product. You can see here they are quite different. If you have beta hydrogen atom, already we have seen the Stevens rearrangement. We have the quaternary ammonium salt. If you have the beta hydrogen atom, the base can deprotonate this proton, and it can lead to E2 elimination in this case, and you will be able to generate olefin and trimethylamine. So, it depends upon the substrate. If you have the beta hydrogen atom, the base can deprotonate, it can lead to the E2 elimination, which can produce alkene and trialkylamine as a product. On the other hand, if you have the alpha hydrogen atom, and it can undergo substitution reaction, it can act as a nucleophile in this case, and then you via SN2 pathway, then you will be able to form alcohol as the product. Now let us look at the reaction of alkyl halide with the triethyl phosphate, and you can see here how this oxygen via SN2 pathway, and so substitution reaction can lead to the formation of the salt, and once you form this salt now, and this Br minus can react this carbon here as via SN2 pathway, and it can lead to the formation of phosphonate, and once you form the phosphonate, you generate alkyl halide as a product, and this is known as Arbozo reaction, which also find broad utilities in phosphorus chemistry. And so once if you have the triethyl phosphate, and which can undergo reaction with this alkyl halide, and you form this salt. Once you form the salt, which can now react with this carbon via SN2 pathway, and which will be the leaving group, and you can generate the phosphonate, where you generate the bromoethane as the product. Now let us look at the preparation of phosphorus ylide, which is very important in organic synthesis. If you want to make alkene, if you have the aldehyde and ketone, and you can form the ylide. If you have the alkyl halide, and you can try to react with the triphenyl phosphine under nitrogen atmosphere. Once you form the salt, this salt now, when you react with base like n-butyllithium or phenyl lithium, sodium hydride, it can deprotonate. You form this phosphorane. Once you form this one, which can make this vacant d orbital of this can make bond, you can form the ylide. Once you form the ylide, which can be reacted with aldehyde and ketone to give this alkene as the product. For example, if you have the this carbonyl compound, it can be aldehyde and ketone, and if you have this phosphorane, which can now readily undergo addition reaction, you will get this betaine. Once you form this one, which can form this cyclic intermediate which can rearrange as shown here to phosphine oxide, and you will be able to form alkene as a product. This has broad application in organic synthesis. If you want to make alkene, if you have aldehyde and ketone, if you have alkyl halide, you can make the phosphonium salt. Once you form the salt, when you can try to react with the base, you can make this ylide. Once you form the ylide, which can readily undergo reaction with this aldehyde and ketone to give alkene as the product. If you look at earlier, we have seen if you have the triphenyl phosphine, you can try to react with alkyl halide and nitrogen atmosphere, you make the salt. The salt is very stable, you can isolate and keep it. Once if you have the salt, you can try to react with the base, for example N-butyllithium or phenyllithium in THF, you make this ylide. Once you form the ylide, in situ you have to add the aldehyde or ketone which can undergo a reaction to give the alkene as a product. Now let us look at their less stable compound, and you can also make the stable ylide. Here you have this carbon ion can be stabilized by the electron withdrawing group. You can make the stable ylide. Once we form this one, this can exist in this form, and this can also readily undergo addition reaction with aldehyde to give the alkene as the product. This is modified Wittig reagent. This is known as Wordsworth-Hemmings reagent. You can make the stabilized ylide which can readily undergo addition reaction with aldehyde to give the alkene as a product. Now if you look at this ylide, this is less reactive with the ketone. It works very well with the aldehyde. If you have the aldehyde, you can try to react and you will be able to make alkene. On the other hand, if you have the ketone, it does not react, very less reactive towards ketone. Therefore, further modification has been done, and you get here. So the triethyl phosphate has been used. If you have this halo substrate, you can try to, as we have seen, you can try to react here. You can make this salt via SN2 pathway. Once you form the salt, now as just we have seen, you can react with the base. Here the use of phenyllithium shown, and it can deprotonate, and you can make this ylide. Once you form this one phosphorane which can now react with ketone, and you can give this, get this alkene as a product where you generate this triethyl phosphate as the byproduct, and which can be easily removed and by washing. And the previous case you have to do the column and to remove the triphenyl phosphine oxide, and this advantage in this can be easily removed, and this also stable, you can isolate and keep it, and in this way which can use for both aldehyde and ketone can be readily coupled to give the corresponding alkenes as the product. If you compare the formation of alkene from aldehyde and ketone, and if you look at the traditional method, if you want to make alkene, you can also make, for example, you have here cyclohexanone, you can try to react with a Grignard reagent, you will get the addition product. Once you have the addition product, you can try to treat with acid and protonation, you can do it, you can form alkene as a product. If you look at here, and in this case mainly you form this major compound. In this case you form this alkene, this internal alkene you generate usually, this exocyclic alkene does not form, it forms only trace amount. On the other hand, if you do reaction with the Wittig reagent, you have this ylide, you can try to react with this ketone, and you can exclusively form the exocyclic alkene as the product. This is the speciality of the Wittig reaction. And if you want to make alkene without rearrangement, for example, and you can take the ketone aldehyde, react with ylide, you will be able to form this alkene. On the other hand, if you want to make alkene using the traditional method, Grignard reagent addition followed by dehydration, and you get this the internal alkene as the product. Now let us look at another interesting example. If you look at here the reaction of this alkene shown here, just we have seen if you have the halo substrate, when you can try to react with the triphenyl phosphine, you can make the salt. Once you form the salt, Now you can try to react with the base. In this case, methoxide has been used, and you can deprotonate. You form the halide. Once you form this halide, now this can undergo reaction with this substrate to give this alkene as the product. Now you look at here, if you compare the previous slide where we compared the reaction between Wittig and Grignard reaction, you can also make alkene using Grignard reaction. You can make the additional product which can further treated with the resultant alcohol can be treated with acid, which can lead to dehydration. You can make alkene and you get the internal alkene. In addition to that, and in the case of Wittig reaction, you can have functional group like ester, but in this case selectively the Wittig reagent reacts with aldehyde. In this case doesn't affect the ester group. On the other hand, if you use the Grignard reagent, and for example you have the here halo substrate, you can make the corresponding Grignard reagent. Once if you have this one, you can add here and you can give the additional product which can further can be treated with acid to give the alkene as the product. However, if you look at here, the Grignard reagent also can undergo reaction with the ester group and you will be able to get alcohol as the product. On the other hand, if you use Wittig reagent selectively reacts with this aldehyde, doesn't affect the ester group. This is the advantage of Wittig reaction. Wittig reaction is an excellent method if you have the aldehyde ketone to make alkene. At the same time, the substrate can have variety of reactive functional group like ester, nitrile group, and they are intact under these conditions. Whereas if you use the Grignard reagent, which also can undergo addition reaction, you will be able to get a mixture of complex products. Now let us look at the selectivity in the Wittig olefination. And just we have seen, if you have the aldehyde and ketone, you can try to react with the halide, you can get the alkene as a product. When you go for the selectivity, whether you get the cis or trans alkene, now let us look at, you have the stabilized halide, you have the carbonyl group, and which can be stabilized, whatever the negative charge can be stabilized by this carbonyl group due to the electron withdrawing nature. This halide is very stable. So for example, when you react with this aldehyde, so you can look at here, this is a reversible. When you carry out the reaction in nonpolar solvent like benzene, and this butane whichever you generate here, which can undergo addition reaction as we have seen, and you have this whatever this one, this is reversible, and therefore it can form the more stable one. If you look at here, the substituent, they are the opposite side due to so they are more stable comparing to this. There will be a steric repulsion here. So you form, since this butane is reversible, it can, even if you form this one, this can go back, you form the stable ones. Once you form the stable butane intermediate, which can lose triphenyl phosphine oxide, then you will be able to form this trans alkene as the major compound. And this always you get, this is minor product. So if you have the stabilized halide, when you react with, for example, aldehyde, mainly you get this trans alkene as the major product when you carry out the reaction nonpolar solvent like benzene. This is just what we have seen the previous slide. If you look at it, here you get the trans alkene. This is because this whatever you have the halide which is stabilized, it can be stabilized by the double bond by delocalization, therefore which can undergo a reaction. You get the E alkene here, the trans alkene as the product. Therefore, if you have the stabilized halide, when you react with aldehyde in nonpolar solvent, the butane which you generate is reversible. You will be able to form the more stable one. Once you form the more stable one, then this reaction takes place, removal of triphenyl phosphine oxide can give this trans alkene as the product. On the other hand, if you use polar solvent, you get usually the cis as a major compound, with trans also you get mixture of compounds if you use polar solvent like DMF in the presence of salt. We will see the next slide in detail. Now let us go for the least stable halide. Just we have seen the previous slide, the halide which has the electron withdrawing group, stabilized halide, which can, if you carry out the reaction in nonpolar solvent, the betaine which you generate addition of the halide with aldehyde is reversible. You will be able to form more stable halide which can undergo elimination of triphenyl phosphine oxide to give trans alkene as the product in nonpolar solvent. Now let us look at this halide, and when you react with the carbonyl compound in polar solvent, you can carry out the reaction in polar solvent, and as just we have seen, this also can undergo reaction. As once we have this reaction and you form this betaine, which once you form this one, and which is not reversible in this case, this is irreversible. So you can now, it can undergo rotation, then you will be able to form this. Once you form this one, this can be removed by elimination. In this way you will be able to form the cis alkene as the product. So if you want to make cis alkene, and what you can do, you can take this, if you have the aldehyde, you can try to react with the triphenyl phosphine, and alkyl halide, you can make the phosphonium salt. This phosphonium salt, once you form this one, you can try to react with the base, you make the halide. That halide can be reacted in situ with aldehyde in polar solvent, and you will be able to form this compound. Once with anti conformation, once you form this one, now it can undergo rotation to give this. Once you form this one, now this can now convert into cis alkene. So if you want to make cis alkene, you can use this triphenyl phosphine based halide. You can try to react with alkyl halide, as just we have mentioned. You can make the phosphonium salt, which you can try to deprotonate using sodium hydride, which once you form the halide, which can undergo addition reaction with anti conformation, you get this, and once you form this one, this can rotate, and which can now eliminate triphenyl phosphine oxide to give the cis alkene as the product. Now let us look at, just we have seen, if you have the unstabilized phosphine halide, when you react with aldehyde, it can lead to the formation of cis olefin, because the betaine is irreversible. As soon as you form the addition product betaine, the reaction of halide with aldehyde with anti conformation, which can rotate and eliminate triphenyl phosphine oxide, it can lead to the formation of cis alkene. If you want to make trans alkene using the unstabilized phosphorants, how will you do it? So one of the ways is, what you can do, once you form this halide, if you have the alkyl halide, as just I mentioned, react with the triphenyl phosphine under nitrogen atmosphere, you make the salt. Once you form the salt, you try to react with the base like sodium hydride, you make the halide. Once you form the halide, you try to react with the lithium bromide. Once you add the lithium bromide, you make this intermediate. You can see here in the presence of lithium bromide, and it can readily undergo reaction with aldehyde. You form this intermediate. Once you form this salt, when you react with base phenyl lithium here, and deprotonation can give this salt, lithium salt. We have this salt now. Once you have this one, now when you protonate using, for example, in this case tertiary butanol has been used, protonation of this can form this butane, more stable butane. You look at here, they are on the opposite side. Once we have formed this one, which can now lose triphenyl phosphine oxide, then you will be able to form E-alkene as the product. So if you have the unstabilized phosphorants, you can make E-alkene, but this reaction you have to carry out at low temperature, negative temperature, and you form this and warm up, then you add this. When you do the protonation here, then it can convert into the alkene. This reaction has been carried out in the presence of lithium salt like lithium bromide at low temperature, and you form this stable one. Once you form this one, which can now, when you protonate and you form the more stable butane, once you form this one, now this can lose triphenyl phosphine oxide to give the trans alkene as the product. So if you have the unstabilized phosphorant, you can make both cis as well as trans. If you want to make trans, you have to carry out the reaction low temperature in the presence of lithium bromide, and as I shown here, then you will be able to make. On the other hand, if you want to have cis, as just I have mentioned, you can use polar solvent. You can form the anti-conformation addition product, which is not reversible. Once you form this one, that can lose triphenyl phosphine oxide to produce cis alkene or Z alkene as the product. Now let us look at the recent development in the Wittig reaction. Just we have seen, if you have the ylide, you can try to react with aldehyde and ketone, you get the alkene as a product. Now let us look at this ylide, which has the methoxy group substituent. It can also undergo reaction of cyclohexanone shown. As we have seen, it can undergo reaction. You will be able to form this vinyl ether as a product. Once you form this one, when you do the hydrolysis, and you can convert into aldehyde as the product. When you do the hydrolysis, and you will convert into aldehyde. So if you want to convert ketone, for example cyclohexanone to cyclohexane aldehyde, you can try to react with this ylide, which can be easily formed if you have the corresponding halide. For example, if you have the bromide, and this, if you have the triphenyl phosphine, you can make the salt. Once you form the salt, you can also deprotonate, and then you form, as we have seen, you form the ylide. Once you form the ylide, now it can undergo reaction, as just we have seen. You get this ether derivative. Once you form this one, when you do the acid hydrolysis, it can lead to the formation of aldehyde as the product. Here another application shown, if you have the dialdehyde, which can be reacted with this bifunctional ylide. Now you have the, if you have so you can react, you form the salt, as we have seen, then you can deprotonate, you form this ylide. Once you form the ylide, you can try to react with this aldehyde. In this way, you will be able to form this cyclic system where you have generate and two double bonds using this reagent. In this way, you will be able to form the cyclic diene derivative as the product. Now let us look at here the reaction of isocyanate with this phosphine oxide is shown, which can undergo reaction as shown here, which can undergo reaction. You will be able to form this intermediate. Once you form this intermediate, it can lose carbon dioxide to give this derivative. Once you form this one, which can further react with this isocyanate as shown here, you form this cyclic derivative. Once you form this one, which can convert into, which can lose triphenyl phosphine oxide, then you will be able to form the carbodiamide as the product. So if you have the, for example, triphenyl phosphine oxide, and which can be readily reacted, if you have the phosphine oxide which can be readily reacted with isocyanate, you can form the carbodiamide. Already we have seen carbodiamide is very important reagent. Already we have seen carbodiamide we use as coupling reagent in the peptide chemistry. For example, if we have this amino acid, when you use the carbodiamide, you will form the amide. This will be converted into urea. So when you take this to like dichloromethane, you can try to couple, you make this amide as a product. In place of amine, you can also use alcohol. If you have the carboxylic acid, you can also use this as coupling agent. You can try to form ester as a product. So if you have the acid sensitive functional group in the carboxylic acid, you can use carbodiamide as a coupling reagent. You can try to dehydrate, you can remove the water molecule which will be converted into urea. You can make ester as the product. And similarly for this, as I just mentioned, we often use the peptide chemistry to make the amide bond. And if you have the amino group and carboxylic acid group which can be coupled and together to give amide, where this is converted into urea as the byproduct. Now let us see some more applications. And if you look at here, in this case the reaction of this nitro derivative with triethyl phosphate is shown here. Here 2 equivalent of phosphate has been used, which can give this indole as the product, and where you generate this triethyl phosphate as the byproduct. The reaction pathway shown here. In this, the oxygen is transformed to phosphorus, it is converted into triethyl phosphate. Here the reaction mechanism shown. So this can undergo reaction, and you will have this intermediate. Once you have this intermediate, now you will lose the triethyl phosphate. You will have this nitroso derivative. Once you have the nitroso compound, which can further react, as just we have seen, which can undergo reaction with the triethyl phosphate, and we will be able to have this intermediate. Once you have this one, now this also can lose triethyl phosphate, and then you will be able to form the nitrene as the intermediate. So in this reaction, you form nitrene as the intermediate. Once you form this one, which can undergo insertion with this alkene, you make this indole as the compound. So if you have the nitro derivatives, you can try to react with the triethyl phosphate, which can convert in the nitro derivative into nitrene. Once you form the nitrene, already we know that nitrene can readily undergo insertion reaction with the alkene to give, in this case, it can produce indole as the product. Here some more examples are shown. This also, this azo compound also can be cyclized, as just we have seen when you react with this triethyl phosphate, excess 2 equivalent of triethyl phosphate, which can convert into nitrene, as just we have seen, which can now cyclize and to produce this. This should be black color, this one, this is here, and you can form the triazole as the product. And now let us look at this compound. This compound also similarly can undergo reaction with this triethyl phosphate, and you form the nitrene. Once form the nitrene, as just we have seen, can react here, and you will be able to form this, then which can further convert into, in this way you will be able to make this carboxyl as the product. So far we have seen some applications using triethyl phosphate. For example, if we have the nitro functional group which can be converted into nitrene, the nitrene can be further utilized for the cyclization to get these nitrogen containing heterocyclic compounds. Now let us look at the reaction of this diol with this thiol derivative, which can, as already we know that, which can now undergo addition reaction to give this carbonate derivative. Once if we have this one which can react with the triethyl phosphate to give this alkene as a product. In this reaction already you know that if you have the diol, that diol can react which can the OH group can undergo addition reaction this can convert into once we form this one, this OH, as just we have seen, it can also undergo addition reaction here, then you will be able to get this can further convert into so thiocarbonate. Once you form this one, this can now react with, as shown here, triethyl phosphate as shown here. In this case it can add here, and this will go here and this will come here, and what you do, you get this and you lose CO2 and plus you get the alkene as the product. This is what you get: alkene, carbon dioxide and thiophosphate byproduct in this reaction. So, if we have the diol, which also can be converted into alkene as using this reagent, the combination of this using these reaction conditions, you can convert into alkene as the product. Now, let us look at the stereoselectivity of the reaction. For example, in this case, you can convert this to trans diol. If you have the trans diol and you can try to react with this reagent as shown here, and you can convert into the trans alkene, you can see stereo specifically you can convert. If you have the trans diol, you can make the trans alkene as the product using these reaction conditions. And as you can see here, this is the selectivity is very high under these conditions. If you have the trans diol, you can convert into trans alkene, and in this case you get this trans cycloactene as the product. Now, let us look at some more examples here. Normally, as you know, if you want to if you have the alcohol, if you want to make alkyl halide, for example, you have the ethanol. If you want to make chloroethane, and traditionally what we do, we try to react with the hydrochloric acid in the presence of zinc chloride, and you will be able to get chloroethane. And similarly, if you have ethanol and if you try to react with the HBr under heating, and you will be able to make bromoethane as the product. And if you have alcohol, you can also try to react PBr3, then in this way you will be able to make alkyl bromide, where you generate this oxide as a byproduct. And if you look at in this reaction, three molecule of alcohol reacts with PBr3, you form and HBr. Once you form this one, the Br minus can react and you will be able to form alkyl bromide plus you get this as a byproduct. So, this can take place via SN2 pathway. So, if you look at all these reactions, you have to use strong acid like hydrochloric acid, HBr, or you have to use PBr3. If you look at the yields are not very good, they give moderate yields under strong acidic conditions. So, if you try to develop method that can be utilized at mild reaction conditions that can give the alkyl halide within high yield will be very useful. Now, let us look at this example. Here the preparation of alkyl bromide is shown here. If you have the alcohol, for example, and you can make this adduct, this can be easily made if you have the triphenyl phosphine and bromine, you can form this adduct. Once you form the adduct, when you react with alcohol, in this case, as we have seen, you form this. Once you form this one, now this can Br minus can undergo ISN2 pathway, and it can generate triphenyl phosphine oxide, where you generate the alkyl halide as the product. So, if you have the bromine and you can try to react with the triphenyl phosphine and you can make this salt. Once you form this salt, this adduct can be reacted with alcohol as shown here via SN2 pathway. You will be able to form the alkyl bromide as the compound. Similarly, you can also make alkyl chloride. If you use chlorine in place of bromine, you can make the adduct. and you can carry out the reaction. Alternatively, you can also try to react. You can react with the triphenyl phosphine with the carbon tetrachloride as shown here, and you will be able to form this salt. Once if you have this one, as just we have seen, you can also try to react with alcohol. You will be able to form plus HCl. Once you form this one, this Cl minus can now react here via SN2 pathway, and you will be able to make alkyl chloride as a product. So, if you have triphenyl phosphine, you can try to react with the carbon tetrachloride. You can also readily form the alkyl chloride as a product and mild reaction conditions and high yield. So, in case of iodide, if you want to make alkyl iodide, the best way is that if you have the diethyl azo dicarboxylate, and you can try to react with triphenyl phosphine. Addition of this triphenyl phosphine to the diazo functional group, as is shown here, can lead to the formation of this intermediate. Once you form this intermediate, this can now undergo SN2 reaction. If you have, for example, let us take methyl iodide, and you will be able to get this derivative. Once if you have the salt, now this salt, when you react with alcohol, let us take this alcohol. So, this alcohol can react as just we have seen, and you will be able to form this intermediate. Once if you have, for example, here counter ion, when it can be converted into Hi, you have this intermediate. Once you form this one, it can rearrange as shown here. It can go here, and you will be able to form this intermediate. Once if you have this one, as just we have seen, the I minus can now undergo reaction here. We have this one, then it can give the alkyl iodide via SN2 pathway shown here, and it can undergo reaction, and you will form the alkyl iodide and triphenyl phosphine oxide as a byproduct. So, you can use this phosphine chemistry. If you have the triphenyl phosphine, you can try to react with bromine, or just we have seen chlorine or carbon tetrachloride. Here you can also use diethyl azo dicarboxylate. You can try to react, and in this way you will be able to form the corresponding halides as a product. If you look at these reactions are milder comparing to the traditional method when you use alcohol with a strong acid like HBr, and you can carry out the reaction under moderate conditions, moderate and milder reaction conditions to give the corresponding halides as a product in high yields. Here the further development in this chemistry shown, just we have seen the use of diethyl azo dicarboxylate in the preparation of alkyl iodide, and now let us look at the recent development, the use of diethyl azo dicarboxylate. If you have alcohol, you can invert the stereochemistry as shown here. For example, now when you react this diethyl azo dicarboxylate with the triphenyl phosphine, just we have seen it can undergo addition reaction, and if you carry out the reaction in the presence of acid, and when addition can lead to the formation of anion which can pick up this proton from this carboxylic acid, you generate the salt. Once you form the salt, now you can try to react with the alcohol. So, for example, you have the optically active alcohol, and we can react as we have seen here, and so which can now undergo addition reaction here, and you will be able to form this derivative, and you lose this one and you form this. Once you form this one, now you have the counter ion here carboxylate which can now react here, and then you will be able to form this ester derivative, and you generate the triphenyl phosphine oxide as a byproduct. This is with the inverted configuration, you can see here by a SN2 pathway. The reaction is stereospecific, and you can generate this substitution product with the inverted configuration once you form this one, and which can now you can do the hydrolysis. You do the base hydrolysis and you get the alcohol as the product. So, if you have the alcohol, you want to invert the configuration, and you can try to use this phosphine chemistry. You can, this is known as Mitsunobu reaction, which has been widely used in synthetic chemistry. If you have alcohol, if you want to invert the configuration, and the best method is that you can try to react in the presence of triphenyl phosphine, carboxylic acid, diethyl dicarbosylate, and you can get this ester with inverted configuration. Once we have this one, when you do the base hydrolysis, and you will be able to get this alcohol with the inverted configuration. The synthesis of allylamine shown here. Already we have seen this reaction when we studied the formation of carbon nitrogen bond. Let us briefly touch this one. If you want to make allylamine, and this is one of the effective synthetic route. If you want to make primary allylamine, you can use this method. Here you can see the reaction of this salt. Vinyl phosphonium salt in the presence of base can react with the phthalimide as shown here. The base can deprotonate, you generate this anion, which can undergo addition reaction to give this halide. Once you form this one, which can undergo addition reaction with aldehyde or ketone here, aldehyde is shown here. Addition reaction can lead to the formation of this intermediate. Once you form this one, as already we have seen, it can lose phosphine oxide. So, once if you lose the triphenyl phosphine oxide, it can make alkene. Once you form the alkene, then you can do hydrolysis, you will be able to get this allylamine as a product. If you want to make primary allylamine, this is one of the effective synthetic route, which involves the combination of Gabriel and Wittig reaction, and you can have this vinyl phosphonium salt. Once if you have this one, you can try to react with this anion that can be generated from phthalimide, the presence of base, which can undergo addition reaction, which can give this halide. Once you form the halide, already we know that which can readily undergo reaction with aldehyde to give this betaine. Once you form this betaine, which can lose phosphine oxide, where you generate this N-alkyl phthalimide intermediate. Once you form this one, there are several approaches are available. You can try to do hydrolysis, and where you will be able to form the primary allylamine as the product. So, this is one of the synthetic route. If you want to make primary allylamine, which we use precursor to make carry out several transformations, and you can start with phthalimide. If you have this vinyl phosphonium salt, you can try to the presence of base and can react. You can get the addition compound, which can react with the aldehyde, and you get this betaine, which can convert into this N-allyl phthalimide, which can lead to this allylamine through hydrolysis, where you generate this phosphine oxide as a byproduct. Now, let us look at some recent development in this phosphorus halide chemistry, which has recently appeared. Now, let us look at this reaction of this halide has been demonstrated with this ester, the presence of chiral copper complex. Here they have taken this copper iodide chiral ligand. When you take this one, it can make complex. Here you make a chiral complex. So, the reaction condition shown here in the presence of base, sodium acetate or ethyl diisopropylamine, which acts as a base. You have to deprotonate, and then in methanol, combination of methanol water medium, and you form this ylide. The mechanism shown here. When you have this, and you have the copper, and you form this intermediate. Once you form this allene intermediate, this once which can now convert into this, this can now undergo reaction with this your ylide to give this intermediate, which can, when you do the, since you carry out the reaction in the presence of proton source and you can protonate this position, then you will be able to get this ylide. This ylide now you have, since you carry out the reaction in the presence of chiral ligand, you introduce chirality here. Once you form this ylide, now this ylide can be reacted with the carbonyl compound here is shown. If you use this formaldehyde, you get this alkene as the product. On the other hand, if you use here ketene, then you will be able to get this allene as the product. So, you can see here, and they have produced this derivative with the excellent optical purities. You can see more than up to 99% enantiomer selectivity. So, this is some of the recent development in this phosphorylate chemistry, and you can see here you can try to react in the presence of chiral ligand, then you will be able to make this chiral alkene or chiral allene as the product with the excellent optical purities. In addition to that, now also there is considerable effort is made to make organophosphorus compound via CH activation. For example, aryl system, you can also try to couple, if for example, if you have the phosphorus compounds, you can make CP bond using palladium based catalyst systems, and you can try to read the recent literature to understand how you can activate the CH bond to make CP bond. And now with this, let us conclude this lecture. In this lecture, we have seen the importance of phosphorus compound. First two slides we have seen the utility of phosphorus based compounds in biological and agriculture sciences. We have seen some of the compounds we use in biological science as a membrane as well as for chemotherapy. Then we have seen some examples which we use as insecticide in agriculture field. So, phosphorus based compounds have broad utilities in agriculture science, biological science as well as material science. We have not seen any examples there. They also broadly utilized to make materials. In addition to that, we also have seen then the reactivity profile of phosphorus in comparison with the nitrogen based compounds. If you look at, although they are the same row, and if you look at here, phosphorus has d orbital which can be used to the bond formation. For example, in the case of ylide, you make the phosphorin which can make bond d orbital involve the bond formation. This is a unique nature of phosphorus comparing to nitrogen atom. In addition to that, phosphorus, you can see here, we start with triphenylphosphine, we convert into triphenylphosphine oxide. The phosphorus 3 can be readily converted into phosphorus 5. In addition to that, we have seen some examples. Phosphorus is prone to undergo strong bond formation with oxygen. We have seen several examples. And this, the unique nature of phosphorus, and this property has been widely utilized in the Wittig reaction. For example, if you have triphenylphosphine, you can try to react with the alkyl halide, you can make the phosphonium salt. Once you form the phosphonium salt, when you react with the base, you can make this ylide. That ylide can be reacted with aldehyde and ketone to make alkene as the compound. And so this is one of the effective synthetic route. If you want to make alkene from aldehyde and ketone, you can make this ylide, and the ylide can be readily reacted to get this alkene stereospecifically with the excellent stereoselectivity. We also have seen how you can control the stereoselectivity. For example, if you have stabilized ylide, you can try to react with aldehyde or ketone in nonpolar solvent, which can lead to the transalkene. On the other hand, if you use in polar solvent, in the presence of salt, it can lead to the formation of cis alkene. We also have seen the use of unstabilized phosphorus halide, the formation of cis as well as trans alkene. If you want to make cis alkene, you can use polar solvent. It can lead, since the butane what you generate is not reversible, it can lead to elimination, give the cis alkene as a product. On the other hand, if you want to make E alkene, and the addition of the unstabilized halide with the aldehyde can generate the anti conformation, which the presence of which can lead to the elimination to give the cis alkene. On the other hand, if you want to make E alkene, and you can try to react the halide with the aldehyde in the presence of lithium salt, and you have the salt that when you react with base followed by at a low temperature, you can make the stable salt. Once you form this one, when warm up, react with the alcohol, for example tetrahydrobutanol we have seen, you can do protonation that can lead to the formation of stable butane, which can lose triphenyl oxide to give the E alkene as the product. Then we have seen the recent development in the Wittig reaction. If you have the ether substituent, you can also try to react with the ketone, which make the vinyl ether as the product. Once you form the vinyl ether, when you do the hydrolysis, it can lead to the aldehyde. For example, if you have the cyclohexanone, you can convert into cyclohexane aldehyde as a product. We have seen one example. Then we have seen the application of stabilized halide, and we have seen how you can form. Then later we have seen the application of this triphenyl phosphine for the formation of alkyl halide. For example, if you want to make alkyl bromide, if you have the alcohol, you can try to react with the bromine, you make the adduct. That adduct can be reacted with alcohol to give the alkyl bromide as the product. Similarly, you can also make alkyl chloride. We have seen one example. Alternatively, you can also try to react. For example, if you have the carbon tetrachloride, you can try to react with the triphenyl phosphine, and you generate the derivative which can be reacted with alcohol, which can undergo SN2 reaction to give the corresponding alkyl chloride as a product. In case of alkyl iodide, what you have to do, you have to try to react the triphenyl phosphine with the diethyl dicarboxylate, which can further undergo reaction with the methyl iodide. For example, when you react this one, it can undergo further reaction. If you have the iodized salt, which can be further reacted with alcohol, then this alcohol can undergo reaction with I minus via SN2 pathway. In this way, you will be able to form the alkyl iodide as a product. Then we have seen the application to the optically active alcohol. If you want to invert the configuration, what you can do, you can use the triphenyl phosphine and diethyl carboxylate. You can try to react in the presence of carboxylic acid. You can make the salt, which once you form this one, which can be further reacted with the alcohol, you make once you form this one, which can now further react with carboxylate, and you get the inverted ester. Once you form this inverted ester, that can be hydrolyzed to give the alcohol with the inverted configuration. Then we have seen the allyl amine synthesis from thalamide. If you have the thalamide, if you have the vinyl phosphonium salt, and in the presence of base which can undergo addition reaction, once you form this halide, that halide can be readily reacted with aldehyde. We have seen one example. You get this butane. Once you have the butane, then that can lose triphenyl phosphonate oxide. You get this N-allyl thalamide. Once you form this one, which can be converted into allyl amine through hydrolysis, in this way you can try to make primary allyl amine as the product. Then we have seen the one recent application in the preparation of optically active alkene, and we are using copper 1 chiral complex as the catalyst. So as you can see here, this organophosphorus compound have broad utilities in organic synthesis, and with this we conclude this lecture. Thank you very much.